Professor Marcelo de LEMOS. He's coming from ITA. That should be something like Instituto Tecnológico de Aeronáutica, Aeronautic Technological Institute, and he's going to talk about advances in mathematical modeling of turbulent transport in porous media. So, please.
So, thank you very much. First of all, I'd like to thank the organizers for this kind invitation. It's a pleasure indeed. It's my first time at IMPA. I was born and raised in the city, but I have never been to IMPA. And just to brush up our geography class, we have a map of the Americas with three important lines: the Tropic of Cancer, Equator, and the Tropic of Capricorn. So the city of São Paulo, and we are close to the city of São Paulo. So we are about 30 miles from the Tropic of Capricorn. When we go to São Paulo to catch a flight, there's a sign on the highway saying you are now crossing the Tropic of Capricorn. So we are at the border of the tropical region, if you will. So I'll say a few words about our institute and our lab, and then we're going to discuss a little bit about some of the stuff that we have been doing for the last few years. IDA started in the late 40s, in the beginning of the 1950s. It was a joint venture, if you will, from the Air Force, Brazilian Air Force, and the Massachusetts Institute of Technology. So at that time, people from the Air Force went up to Cambridge, Massachusetts, and invited 7 people from MIT to come to Brazil and put together a plan for having an engineering school that eventually in the future would get us an aeronautical industry. So that was a very nice long view. And in the beginning, we had professors from 12 countries and a very strong connection with the American educational system. So those are our first principals or rectors, if you will. And the first one was Professor Smith. Professor Smith at that time was the head of the aerostructural department at MIT. And the fifth one, and this fellow, Johannes Meyer, if I'm not wrong, he was of Dutch origin. He immigrated to the US after the First War. And Professor Cecchini was the first Brazilian to become a rector of ITA, and he was actually born in France. So he's 90, and he was awarded an emeritus professorship status just a couple of weeks back. So this is our history. And so ITA provided the conditions for establishing late in the 60s of Embraer. Embraer is the Brazilian aircraft company. And over the last 40 years or so, Embraer has become the third largest commercial aircraft manufacturer. We're talking about mid-size aircraft, 100-seat class. So the three other manufacturers are Boeing, bigger ones, Boeing, Airbus, and Bombardier. Actually surpassed Bombardier. We are the third now. So our biggest competitors are the Canadians, actually. We don't compete with Boeing or Airbus. So ITA was conceived to support a future aeronautical industry in Brazil, but today research and development has spread over other areas as well. So ITA is, we only graduate engineers. We have 600 undergrad students and 1,200. And we graduate aeronautic engineering, electronics, civil, more devoted to airport construction, if you will. Computer engineering and mechanical engineering, and also evolving energy. Most of our students, they used to go to Embraer. Now they are all over, actually, all over other areas as well. And this is actually our new lab. I have a folder at the entrance there. So this was a gift of our beloved Petrobras. Gave us a new building, and the building is nearly ready. We have a 65-seat auditorium, and I would like to make that available to the MARCELO Brazilian chapter. So we can have maybe in the future. The building is not ready yet, but we are almost there. So it's going to be a pleasure actually to, whenever you folks are in São Paulo, we'll be delighted to have you visit. So the lab, what's called the Computational Transfer Phenomenon Lab, this is linked to the Department of Energy. I'm now serving as the head of the Department of Energy. So we started activities in 95, we became official in 99, and our mission statement is support computational activities needed for R&D projects involving numerical solution of heat and mass transfer. So this is our mission statement. This is something that we have been done for the last 15 years or so. Those are my graduate students, former graduate students. So we have put together a few papers. Thanks to the Lord, we have been cited in the literature, and a few books as well. So and once in a while, we get away from books and papers and get a nice Brazilian-style barbecue. And after my years of teaching, I am definitely convinced that the left-hand side of this slide is correlated strictly with the right-hand side. So, talking about mathematical modeling of flow and heat transfer in porous media, we're going to talk a little bit about the applications for that, modeling, the microscopic computation, macroscopic computation, model, and some results. Hybrid systems we're talking about finite porous medium, something that ends, and then there is a clear flow, right? So, environmental flows. So the kind of porous media that we're talking about is not actually flow in rocks or sand or something like that. So this is the Amazon River and the Amazon jungle right there. And you see we can have an atmospheric boundary layer, and through the forest we can have what we call it a permeable structure. So flow through vegetation and trees and flow over populated areas where you have buildings, trees, whatever. So that can be seen, mathematically speaking, if you look from far from the site, that can be seen as a permeable structure. As far as engineering application, engineering flow is of some concern. So we have a gasifier here. So gasifier, usually you have pellets of something, or coal. In our case, in Brazil, biomass, for example. So you have gas going in one direction and the pellets coming in the other direction. And here's a reactor for producing hydrogen-rich gases, if you will. If you have a rich mixture coming in, you can have a partial oxidation followed by a thermal reformation. So you get a hydrogen-rich, and this is a porous structure, a hydrogen-rich stream. So this is a way of producing hydrogen. And this is a porous combustor that has been used for heating, household heating, actually. So we're going to be talking a little bit about applications on those particular equipment. So when we talk about flow in porous media, so we have a solid phase distributed somehow in between these solid particles. We have void space. So we can have volume average that are defined like this, and the porosity, which is defined as the ratio of the void space to the total volume. So the very first thing is to establish some volume over which we're going to make an average. And we can also have a characteristic number, which is the Reynolds number, based on the statistical value of the pore. So those are the basic models for flowing in porous media: the Darcy model, the Brinkman, including the viscous term, we divided by the viscosity already. The Forkheimer, including the nonlinear term. And this is a more complete model, if you will, is the unsteady volume average Navier-Stokes equation plus the two extra forces. So when a body of fluid goes through some solid material, the fluid feels two extra forces. The first one is due to viscosity, because the particles, they stick to the surface. And that depends on viscosity. This is this first term here. It depends on viscosity. The second one is that the pressure field before and after the solid structure is different. There is a wake formed after passing the solid. So the difference in pressure gives rise to what we call the form drag or pressure drag. So that depends on the pressure field surrounding the surface. So we have also a problem with scales, right? So if the size of the voids are too small compared to the size of the solid, if you will, so we will not have what we would say a turbulent flow. So we are talking about things like this, where the void is sufficiently large for having a turbulent flow inside this permeable structure. So I prefer sometimes to call it permeable structure, not a porous medium, because you think about the sand or rock. So if we plot the flow regimes, and this is porosity, one means clear flow. There's no solid in between, distributed in the field. And if we plot the Reynolds number here, we see that in the literature, you can clearly have models for laminar flow, we all know that, and the transition to turbulent flow is quite clear. So, if you start having solid material distributed, the more material you have, so you have laminar flow in porous medium. So we look at the literature, and we figured that there was a range in this flow map that had not been studied that much, which is very large Reynolds number with a very large porosity. So the flow was turbulent, and we had the solid phase distributed. So we start to look at in this range and how we could mathematically model it. So we knew two things. First, we have a solid phase distributed, so we need to do volume averaging. We have to apply to the equation instantaneous, local equations, the volume average operator. And because things fluctuate in time, we have also to apply time average the mathematical operator of time averaging, if you will. And we start looking at the literature, and there was a huge debate in the literature, because some researchers would say that, well, we have to first do time average and then volume average to get the right equations. And there was a huge debate, and two groups were fighting against each other. The one was a group led by Akira Nakayama, professor at Shizuoka University. And the Japanese group said, well, we gotta do first time volume, time average, and then volume average to get the right equations. And then the American group, led by Professor Lage at the Southern Methodist University over in Dallas. So the American group said, no way, you folks are all wrong, because you gotta do first volume, and then time average, and then you get the right thing. And the people would write nasty letters to the editors. And we look at that, and then the Brazilians came around. We decided to look at the way the equations were put together, and we came up with something that we call the double decomposition concept, which is split in time and volume at the same time. So we did that for the flow, and then we did that for non-buoyant heat transfer. We did that for buoyant heat transfer, for mass transfer. We include double diffusion, and lately we have also included the movement of the solid matrix, which is applied to gasifiers, for example. So going over the operators, so we all know that what's a volume average operator. So a volume average is defined like this. So the gradient, the divergent, and the time rate can be, these entities can be volume average, and this is the result, so you all know that. So any quantity can be split into a volume average and a spatial deviation. Spatial deviation is the difference between the local value and the volume average, right? So this is standard definition of volume averaging. And then we decide to look at time average. Well, time average is defined like this. So any quantity can be split. So we are talking about things that fluctuate in time. Any quantity can be split into a time average and a fluctuation. And these two operators, they commute. So the time average of the volume average, is the volume average of the time average if the two domains of integration, space and time, do not depend on each other. So if we're talking about shrinking or swelling, forget about this, or vibrating. So then you have porosity depending on time, so we can have it. So everything that is written in here is for having an independence of integration domains. So, so what we proposed back in the early 2000s was to do the following. We start with a standard volume decomposition, and we took each one of those parts and split in time decomposing, in time, if you will. So we end up actually with 4 guys instead of 2. And if we start first with time decomposition, and we split each one of those 2 guys into volume and a deviation, volume average and deviation, we also end up with 4 guys. So instead of splitting in 2, doing volume average, and in 2, doing time average, we split them in 4. And they have equivalences. And here is the concept. Let's say that AF is a general vector quantity. So if we do volume splitting first, volume average, we have AC and CF. We add these 2 vectors and get the same quantity, AF. And let's see that we take this guy and split it in time, and we take the deviation and split also in time. So we get 4 vectors that add up to the same general quantity. And below here, we do the other way around. We first split in time, and we have fluctuation in time, and then we apply the second operator, which is volume averaging. And we can see that now we follow the line A, B, E, D, F. So if you apply the 2 operators independently of the order, they can be represented by 4 guys instead of 2. And we have an equivalence here. As you can see right here, time average of volume average is volume average of time average. And here you see lines B, C, for example. The fluctuation of volume average is the same as the volume average of the fluctuation. This picture gives us this idea. And you see this line, CD is equal to BE. That means the time average of the deviation is equal to deviation of time average. So with those equivalences, we decided to go back and using this mathematical framework, we decided to go back and rewrite the equations and to see why the Americans and the Japanese were fighting about. So we started, this is the local instantaneous equation, momentum equation. So we applied first, so if we decide to go first order, we decide to go time and then followed by volume. So then we apply the standard time average, and we get the Reynolds stress tensor, which is usually get in a turbulence modeling. And then we volume average this equation. So this is the volume average Reynolds average Navier-Stokes equations. And then we end up with two extra terms, which are those two extra drags, and something that we call it a macroscopic Reynolds stress, because now we're talking about a volume, right? And then we decide to go back and reverse the order. Let's do first volume average. So we started again. Starting point was instantaneous momentum equation, and we did volume average, and end up with this equation. This is the volume average equation. And then we time average, and end up with the very, very same equation. So we say, what the heck? It doesn't matter which order you use, you get the same equation. Why are these people fighting? So and then we look at the convection term. In the convection term, there is a dyad here, velocity times velocity. And because we can now split each one of these vectors in four guys, so the time average of the volume average of this guy ends up to be 4 people, 4 guys, instead of only 2. And here we have what we call a dispersion, a macroscopic Reynolds stress, and the convection, standard convection, and an additional guy. So our convection term splitting in 4 using the 2 operators, using this mathematical framework, end up to be composed by 4 entities, if you will. A convective term of macroscopic mean velocity, turbulent stresses, similar to standard turbulent flow. Dispersion, what we call a dispersion, is a correlation between deviations in our mathematical framework. So dispersion for us is a correlation between deviations. And then we end up with this 4th guy that we call a turbulent dispersion. So if the flow is turbulent, so this guy, there is an extra term. Usually, well, in laminar flow, there's dispersion, right? In turbulent flow, there's turbulent stresses. So in porous media flow, in turbulent flow in porous media, we have the so-called turbulent dispersion. Or at least we were able to identify it. So we decide to look at the way the turbulent kinetic energy was put together by the 2 groups, because the mean equation, the momentum equation, we had no difference. So how do we form an equation for turbulent kinetic energy? Well, first we have to have a transport equation for the time fluctuation, and you multiply it by, you take the scalar product by the time fluctuation and time average. Then we end up with this guy. This is the K. K is already, the turbulent kinetic energy is the outcome of a time averaging process, and we volume average. So we end up with this guy. This is the turbulent kinetic energy following time and then volume averaging. And then we decide to go the other way around and take first the volume average and then the time average approach. So we start with the macroscopic transport equation for the fluctuation. So we volume average the time, the fluctuation. And then to compose the turbulent kinetic energy, we apply the scalar product. So we multiply it by itself, by the volume average of U prime, and end up with this guy. So this is another way of identifying a turbulent kinetic energy with the flow. And then we look at 2 ways and say, wow, bingo. This is where these 2 groups are different or are doing something different. The Japanese were talking about the first guy, and the Americans were talking about the second guy, but they did not have the mathematical framework to explain the difference. So there is an extra turbulent kinetic energy. If you double decompose, there is an extra term that we call it the extra turbulent kinetic energy that differentiate the 2. And then we published that in 99 and then another paper in 2000. So when you don't have the right notation or the right mathematical framework, you end up, not finding things. It's interesting how notation plays a role in developing things. So because we had this notation, so we put together this double decomposition, so we were able to find the difference between these two ways of viewing things. And then we decided to establish a macroscopic model for turbulent flow in porous media. So we start with the standard K equation, turbulent kinetic energy, with volume average. And we included an extra term, a production term. So when a flow comes and goes through some solid material, it gets perturbed. If the flow is laminar first, it gets perturbed. Some of these mean mechanical energy is converted into turbulence. So in our model, we included an extra term, and as all turbulence modelers do, we had an unknown constant to be determined. So what we did is, in the equilibrium situation where production equals dissipation, you can, let's say, get an equation like this. And once you have the two sides of this equation, by integrating unit cells, you can determine this constant. So what we did is we assumed that our porous medium was made by an infinite number of those unit cells. They could be made out of elliptics, longitudinal ellipses, circular rods, and transversal ellipses. And we had also some computations done by the Japanese group for square rods. So what we did is we compute the fine flow in here and integrated numerically. And we put together in a plot, and here's the K values, and here's the epsilon values. And this is for a whole bunch of Reynolds numbers, for geometries. And we see that we can have a straight line here, and that straight line here gives us a number of 0.28 for that unknown constant. So with that, we close our model, if you will. So regardless of the shape of the porous medium, regardless of the Reynolds number, we got one number for our constant. And so that was a nice indication that we are not all that wrong. I say we might be wrong, we're limited, but at least we got something that made sense. And here's a plot that shows the value of turbulent kinetic energy related to the Reynolds number. And the amount of turbulent kinetic energy that you have, that depends on the shape of the Reynolds of the porous medium. So if we have a more streamlined flows, those triangles are for the longitudinal ellipses, so the flow is more streamlined. So you have less mechanical energy converted into turbulence, and those higher value here, those are for the transverse ellipses, that you have a huge wake behind the ellipses. So regardless of the geometry, so we had something also that made sense. So we decided to rewrite all transport equations applying these two operators and see if we can get some meaningful results or some advantage. So this is a plane channel flow with a sudden expansion. And if you have a plane channel flow with a sudden expansion, we have two large recirculating bubbles. Having a large recirculating bubbles in a flow means that you are losing energy because you are transforming some mechanical energy, mean mechanical energy, into turbulence, and then you lose energy. So our idea was to, let's see if we, right after the expansion, we put some stuff in here with some porous material, what's going to happen? So in doing this, we kill the recirculating bubbles. So, but you might say, well, you are including some sort of obstruction in the flow. We are including some sort of porous material there. Huh? Yes, but we lose in here and we get in there. So the net gain is advantageous. The other thing that we did was we look at the shell and tube heat exchangers. You might be aware of that. And in shell and tube heat exchangers, we have baffles. So the baffles, they push the flow up and down across the rods, right? We have one fluid come inside the tubes and the other one over the tube, over the shell. So the idea was, those baffles, they are made of solid material. So our idea was, how about if instead of solid material, we had some sort of perforated plate, like a porous structure? So the flow can go through more easily. Okay, you don't exchange as much heat because the flow is not that much transverse to the tubes, but there is a net gain. We don't get enough, as much heat exchange, but to pay much less pumping power. So there is a net gain on that. The other thing that we look at geometry is that we decided to study impinging jet into surfaces. So there was a nice measurement, experimental work done in South Africa. The guys, they impinge some jet into a porous layer through a disk, and there was a clearance around where the flow could come up. So the idea is, if we apply this model, are we able to correctly simulate the flow inside this chamber, if you will? So those are the results. Now we turn 90 degrees around, and the flow is coming horizontally. And those are the calculations done by the group at South Africa. Those are ours. And those are measurements. The measurements are done only on the empty space, not inside the porous form. They use laser Doppler velocimetry. So you can see here that the center of the recirculating bubbles in our calculations are closer to the experimental work. So that was a very nice indication. So we move on and try to do some heat transfer, because we have many technological applications for that. Let's say that we have a surface, and one of the applications for impinging jet is you want either heat or cool that surface. So you have an impinging jet coming with a temperature T0, T sub 0, and the plate has a temperature T sub 1. They are different temperatures. And the question that we had was, if we covered the layer, the down plate, with some sort of porous structure, can we get more heat or less heat? If we can get more heat out of this surface, bingo, it's nice. So we did these calculations, and this is a plot. This is porosity of the layer, and this is a ratio of Q dot is amount of heat with the layer, with the porous layer, and Q dot clean is without the porous layer. So whenever this ratio is higher than 1, yes, indeed, it's a very nice idea to cover that layer, that plate with some porous structure. Actually, we increase the surface, the heat transfer area, actually. So at the end, you do that. And then we decide to include some chemical reaction to calculate our porous burners. So this is a silicon carbide sort of material. And this is a flame inside this silicon carbide. So you pump in some mixture of methane and air, or some hydrocarbon, and ignite it. Instead of a free flame that we have in our oven, or in a candle, for example, we have a flame that is inside this material. And because it's inside, it heats up the solid part. So here we have the gas temperature coming in, and here we have combustion. The temperature of the gas goes up. But because this is inside a solid material, heat flows back by conduction, and here's the solid temperature, which is higher than the gas temperature. So it heats up the gas. So heat is recirculating. So the average temperature is higher, and you use less fuel for producing the same power, if you will. So there is a regenerative sort of effect. So those are burners, commercial burners that have been used in, for household applications and also for drying in paper and pulp industry. So we did some calculations using here the 1 EEM that I spoke yesterday. So in this particular situation here, we have only one energy equation that considers that average value of the temperature for the solid and for the gas is the same. And as we pump some more air, we are increasing the velocity here, the coming in velocity. So this is the flame front. So the flame front is pushing forward and opens up. And at the center here, we have unburned gas coming out, for example. And down here, we have one-dimensional calculations compared with the experiment. The blue lines are experimental measurements. And in here, we use the two energy equation model. So we have an energy equation for the gas and one energy equation for the solid. And you can see here that the temperature of the gas in the flame front is higher than the temperature of the solid, as we expected. So in situations where, in these particular situations, where we have industrial applications, I'm not talking about maybe in situ combustion, it may not make a difference. But in those situations, it does make a difference. And the reason why we did not get this reduction in the temperature here, because we did not have the appropriate boundary condition when we did those calculations, because you have to have a radiation boundary condition. So at the exit of the burner, you have to include the radiation to the environment. So we have more recent calculations that show that effect. And then we move on and then decide to calculate things when the solid matrix moves in relation with the fluid. And applications for that are for gasifiers. So here we have a solid velocity and the Darcy velocity. Remember that here, Darcy velocity, we have two adornments here. The first is subscript T, which means that it's a Darcy velocity. We took the volume average, and we have a bar, which means that it's a time average. So in this particular case, we assume that the solid moves at constant speed. So you can have two situations. They can either move in the same direction or in the positive direction, as you have in gasifiers, for example. And then when we always have a relative velocity. So a relative velocity for a counterflow is larger than a relative velocity for a parallel flow. And we got these temperature profiles for both phases, for the solid and then for the fluid. And they follow expected behavior, if you will. And that's it. I guess that covers a little bit what we have done.